Alright guys, today we're going to talk about antiderivatives, also known as indefinite integrals. And that is an equation whose derivative is equal to the original equation that's given. So let's do a real simple example. With an original equation that's just y equals 3. That's about as simple as it gets. Okay? And so, an antiderivative of y equals 3 could be y equals 3x, because if I took the derivative of y equals 3x, then the derivative of that with respect to x is just 3. But the antiderivative could also be y equals 3x plus 2, because if I take the derivative of 3x plus 2, that will also equal 3. It could also be y equals 3x minus 7, because if I take the derivative of 3x minus 7, that will also equal 3. So as you can see, when you're taking an antiderivative or an indefinite integral, there is actually more than one correct answer. But we represent it this way. So if I am taking the indefinite integral of 3 with respect to x, then my answer has to be 3x plus c, where c just equals any number. What c really stands for there is a constant, because if I'm taking the integral of 3 with respect to x, then the answer is just 3x plus some number. So we represent that 3x plus c. So just like we have some generic rules for derivatives, we also have some generic rules for integrals, and the only one I want you to know for right now is this one right here. If you are taking the indefinite integral of ax to the n with respect to x, the answer will always be ax to the n plus 1 over n plus 1 plus c. And remember, that c just stands for some number. So let's look at a couple of examples. So first we have the integral of 2x cubed with respect to x, and so following our rules is going to be 2x to the 4th, because 3 plus 1 is 4, divided by 4, which can be simplified to just x to the 4th over 2, and then don't forget your plus c. Alright, let's look at one more. So let's say we want to take the integral of 5 with respect to x. Now if we wanted to, we could write it the second way, of 5x to the 0 power with respect to x, and of course x to the 0 power just equals 1, so that's just a funny way of writing 5. But I wrote it that way so we can follow our rule. So once again we're going to go ax to the n plus 1, right? 0 plus 1 is 1, divided by 1. And of course the simpler way to write that would just be 5x, and then don't forget your plus c. So whenever you're taking the integral of a constant with respect to x, it really just ends up being that number times x, and then plus c. Alright, so we also use the term definite integral, and a definite integral is used to find the area under a curve between two x values. So today we're going to look at this example. And what we've written there, we see the same sign we've been using before, but now we see a 1 and a 3. So what I've really written there is, what is the area under the curve of 1/2 x squared between the values of x equals 1 and x equals 3. And before we solve that, we're going to actually look at a graph of 1/2 x squared, and we're going to look at a way to approximate that area. And then we're going to see that by evaluating the integral, we can get a better value for the area under the curve. Alright, so here we have a picture of a graph of y equals 1/2 x squared, and I really need kind of a better version of this area right in here. I'm just going to sketch it. So if I look at that, I've got 1, 2, 3, and if I look at my y-axis, I'm going to go 1, 2, 3, 4, 5. Okay, and of course when x equals 0, y equals 0, and when x equals 1, y is going to be 1/2. When x equals 2, y is going to equal 2. When x equals 3, y is going to equal 4.5. And so our curve is going to look something like that. So if I wanted to approximate the area under the curve, what I could do is split this up 1, 2, 3. I can make a rectangle between 1 and 2, and a rectangle between 2 and 3, and then this top part I can approximate as triangles. And what we're going to see is when we calculate the area of these rectangles and triangles, that's actually going to be a slightly bigger value than the area under the curve, because we're treating those edges of those triangles as straight lines when in fact they're really curved lines that curve kind of inside the straight line. So the value that we get approximating it this way is bigger than the true area under the curve. But if I do that, then I'm going to find that the area of this rectangle right here is just going to be 1/2, because it's 1 times 1/2. And the area of this triangle right here is going to be 3/4. Of course, the area of this rectangle here will be 2. And the area of the triangle up top is going to be 1 1/4. And if we add all that up, the total area of my rectangle and triangles is going to be 4 1/2. And like we said earlier, that's actually slightly larger than the area under the curve. So let's look at evaluating it the more accurate way. So if we're evaluating the integral from 1 to 3 of 1/2 x squared with respect to x, then following our rules, we're going to get 1/2 times x cubed divided by 3, which just simplifies to x cubed over 6. And then we usually put that plus c like we did earlier. We're going to talk about that in just a second. And then we show this, we're going to evaluate that from 1 to 3. And that's the way we show we're evaluating that from 1 to 3. Now typically that c is not shown, and let's talk about why. When we want to evaluate that from 1 to 3, what we're going to do is plug in our top value first. So it's going to be 3 cubed over 6 plus c. And then we're going to subtract our other value, which would just be 1 cubed over 3 plus c. And so what we see there is we have a c minus another c, and those cancel out. So typically the way that's actually just going to be written is just x cubed over 6 evaluated from 1 to 3. And we'll just put in 3 cubed over 6 minus 1 cubed over 6. 3 cubed is 27. 1 cubed is 1. 27 minus 1 is 26 divided by 6, which is also 13 divided by 3, which is also 4 1/3. And that answer agrees with what we talked about on the last slide. On the last slide we got 4.5, and we said that 4.5 was actually just slightly too large. It was an approximation, but it was too big of an approximation. The actual value for the area under the curve for 1/2 x squared dx is 4 1/3. And you guys can probably already guess how we're going to be using these integrals in physics when we're dealing with areas under the curve and we're dealing with velocity and position and acceleration. And we'll talk about that in class tomorrow.